can start. Okay, it's a transition to an open source solution, but more heavy, I would say, in terms of technology. So probably the audience was coming from different sciences. In this topic, we are going to speak on technologies applied to definitely to computer science and to mostly orchestration technologies related to Internet of Things, Edge Cloud, but also let's say 5G and 6G networks. So my name is Anastasios Zafeiropoulos. I'm coming from the National Technical University of Athens, specifically the Network Management and Optimal Design Laboratory. And we are going to speak about intent lifecycle management. So coming to the domain of orchestration, whether we have compute but also network resources, we want to deploy services and applications, and we want to manage their life cycle in terms of provisioning and resource management. So for this, in many cases, we have a request. So we have an intent that has to be satisfied and processed in order to manage the application in a way that the provider will be happy, but also the one that provides the resources will optimize the way that the resources are used. This may be related to cost, to energy, to optimal performance, whatever. So for this, we have adopted the intent definition coming from IETF RFC 9316. So we have intent defined as a set of operational goals and outcomes described in a declarative way. So we have this definition, but then the way that you implement and you manage the intent is dependent on your implementation. So we can consider that we have a high-level expression of objectives and constraints that have to be satisfied in the way that we manage this deployment. And for this, we consider critical to have semantics, actually a knowledge graph, that we can represent the information to manage the intent. Okay, in this figure, in this diagram, we try to see how we can model such info. I will try to go shortly through it, just to give some highlights. Okay, we have graphs. We call them application graphs, we can call them service graphs. It's a graph with a set of components interconnected that we want to have different type of deployments for these graphs. And these graphs have components, so we interconnect components, and these components are connected through relationships. And for each type of them, we may host information related to their type, if they are classified as computational heavy, memory intensive, network intensive, and it goes on. And this type of applications, they are somehow classified. Whenever they are deployed, we have an application graph instance. So this is running. It has to be provided over resources. So then we speak about deployed components and deployed relationships. And for each case, in the deployment, we have an intent. I want to deploy a media streaming service and achieve high performance or achieve low energy consumption as much as possible. So then, the combination of the application graph instance with the intent is translated to requirements for the components and for the relationships, both computational requirements and network requirements. And this has to be deployed over infrastructure. Infrastructure is coming on the right part of the figure from infrastructure providers. So we have cluster nodes and network links that interconnect these cluster nodes. And this goes on, application is deployed, we collect a lot of data, we process them, we check if we have good intent status or we have violations, and we can proceed to corrective actions. So the important thing here is that information from different types of deployments is mapped to this graph, this knowledge graph, and then we have it available for future deployments, for runtime actions. So we are learning from the continuous operation of the network and computational infrastructure. So we consider this very, very important for the scenario. And then we move on to this figure where we have 3 control loops in the life cycle management of the intent. Okay, first control loop is I get a request, I have some high-level objectives, constraints, and the application graph, and I want to translate it, so this can be also done, let's say, with generative AI tools, to a formal intent description. And I can also do kind of conflict resolution. If you ask me things that are conflicting, I can notify you that, come on, this you have to improve in your request, so to have a good intent description. So this first control loop does this syntactic and semantic validation. Then, having this, we have a valid intent, we move on to deployment. So we have infrastructure coming from multi-providers. So control loop 2 actually supports solving of an optimization problem. What is the best way to serve this intent based on the offerings of multi-providers, and it gives a solution, and it also supports runtime management. Okay, I see that my intent is not well satisfied, so I want to do customization. So control loop 2 does all these things in runtime, and control loop 3 actually provides long-term feedback. So intent is processed, I get intent reports, I can see what went well, what went wrong, and I can do customizations. And in all control loops, we share information in the knowledge graph already mentioned. So we can take advantage of reasoning, recommendations coming from the knowledge graph for this purpose. Now, for this, we have developed a simulation kit, okay, an open source kit that we try to support different type of deployments with dynamic creation of multi-cluster infrastructure, dynamic creation of application graphs and application workloads, so as to be able to experiment, let's say, a lot with different type of graphs and infrastructure. It will be really hard to do this on real infrastructure because we need a lot of resources, and also playing with different type of graphs and microservices was really hard. So we decided to develop a simulation kit and maintain it for this purpose. And based on the deployments, we assessed three main metrics related to intent violations, acceptance ratio of the request, how many of the requests are properly served, and metrics related to costs in terms of CPU usage and also energy consumption. And moving one step further, for this simulation kit, we are working on making an agentic version for this. So here we said, okay, we have a complex setup, we have different control loops. Let's try to train agents to support us in the different parts of the process. So again, we have an intent definition. We have generative AI tool supporting the first control loop with the intent translation, and we have different agents supporting deployment and scheduling, adaptation on runtime, and continuous monitoring and reporting. And for all of them, we have, as said, the knowledge graph, storing knowledge, learning, making suggestions. So reasoning is supported, and all these agentic workflows are exploiting the reasoning part by the knowledge graph. And for sure, for resources, we speak up above the overall computing continuum, okay? Considering also radio resource units and 6G technologies, and moving to the edge and to the core part of the infrastructure. And this is, let's say, a high-level figure of the agents. Okay, we have a supervisor agent managing the requests and having different tools for the initial intent management. The intent agent supports conflict resolution, semantic and syntactic validations, and proper creation of an intent manifest. We have the deployment agent that actually is the one managing the deployments with the runtime adaptations. We have provider agents that are actually providing resources and managing the part of the providers, and the knowledge graph. And in each of them, we have different control loops activated, as said in our previous work. And in the agents, we combine large language models driven decisions, but also rule-based logic. And in some cases, we work also with reinforcement learning. So agents are of different types and combine different types of decisions to satisfy the intent. Okay, and coming to, just to show some of the results, prior to the agentic approach, with the simulation kit, we work with assessing intent violations during the time slots by activating the different control loops. So the green light is what happens when we have no intent control loop activated. So let's say baseline. And then by activating different loops, we can see what is the impact in terms of a reduction of the intent violations. And we have done this for different objectives. In one case, my intent was give me this service with the highest performance possible. And in the second case, give me this service considering the lowest energy consumption. Okay, and the lowest line in both cases is the one with the all control loops activated. So we see a major improvement in the reduction of intent violations. Then, having this, we also checked how the deployed components change over time. So, in one case, we asked to have high performance, in the other, energy efficiency. But the providers are classified in three categories. I have a provider that internally wants to support intents targeted to high performance. Another provider wants to have a moderate cost. And another provider wants to be energy efficient. So in the first case, we saw that most of our components want to the performance-oriented providers. And when this is, let's say, over full with request, then we have requests going to the others, and the opposite in the other case. And now, having assessed the simulation kit, what is important is also moving to the agentic approach. Okay, so here we have three lines. The blue is the non-agentic, the one with the simulation kit. The orange is the agentic approach without the use of the knowledge graph, with an empty knowledge graph, so it's agentic empty. And the green is the agentic approach with a populated knowledge graph. So we have knowledge that we take advantage in our decisions. And what we saw, actually, it's clear that non-agentic approach, we had this type of violations. This percentage was reduced a lot while moving to the agentic approach, and much better while moving to the agentic with knowledge graphs. So we saw a very high percentage of improvement, and we assessed also different type of metrics on the behavior of the agents in terms of reliability, automation, capacity for adaptive management and energy efficiency, but also continuous learning, because we assessed it by just populating the knowledge graph with 3-4 deployments. It's not that we populated the knowledge graph with a mass history of data. So results can be further improved if we consider an operation running in a larger period in time. And for sure, okay, there is a lot of ongoing work. We want to add more metrics rather than CPU usage that we mostly consider at the moment. We want the agent to support more orchestration actions, so to support also scaling and other type of actions. We work on a game theory approach to support negotiations and auctions between the intent agent and multi-providers. So we have offerings and we have negotiations in trying to, let's say, simulate a real ecosystem of multi-providers that offer resources, and the agents take place how they manage them. And also development, extension of the knowledge graph to what is called a context graph that is also support tracing in the decision making, why the agents took this decision and if it was successful. So I can learn also from the decisions of the agents. And that's all on my side. Okay, this work is done as part of the 6Green 6G SNS project, but is applicable both to 6G resources, but also in general computing continuum. We'll be glad to discuss for any question or feedback from your side.
Thank you.
Thank you.
I don't know if we have a question. No? So we can move on. Don't give work to him.
So slide 10, please. Okay. Slide 10. Can you show slide 10?
Sorry, slide
Yes.
10.
Yeah. So what is really interesting is this thing here. Okay. So using agents with knowledge graph. Okay. So here you only have prediction. Here you have prediction plus determinism, because the knowledge graph are providing the deterministic thing. So this is important. So actually we need to promote this as an architecture pattern. Sorry for that, but I need to work with you on this, because this is really, and you have to know that we might be about to launch in SC42 a project on multi-agent framework. I asked to call it multi-agent reference architecture, but we'll see. It's launched by Korea. It was this morning at 2 o'clock in the morning. Okay. So, and I asked to be created, and this is an example.
Sure, Antonio, many thanks for the feedback. We can definitely discuss as an example of multi-agent approach. Many, many thanks. Any other question?
If not,
no? Thank you very much.